Seems more people are entering, so let's wait a few more minutes and then we can get started.
It's the advantage when you teach large courses.
Yeah,
you have a bit more reach.
That is true. Okay, I think I can start with the introduction. So welcome everybody. So to this next talk on the DIGA webinar series. So it's my pleasure to introduce Alex Jung from Aalto University. Alex obtained his PhD, that was back in 2012, from the Technical University Vienna. There he also did a postdoc as well as at ETH Zurich. And then he joined Aalto University, that was in 2015, where he is now leading the group on machine learning for big data, thereby mainly focusing on network structured data. So I think he's a very good fit to this webinar series. He also won several awards and currently also serves as an associate editor for the IEEE signal processing letters. He's also chairing the IEEE Finland joint chapter on signal processing and circuits and systems. And judging from his profile picture, he also has some relationship to Mexico apparently, but maybe he can talk about that later on. So I'm looking forward to your presentation, Alex, so go ahead.
Thanks a lot. It's really a pleasure to be here. Yeah, basically the profile of myself you have already heard. Just a quick overview of our research agenda. So as already mentioned, we are working on machine learning for network structured data. Our current focus is on network federated learning, but somewhat a very recent sideline is on explainable machine learning. So I will not have time today to talk about this, but this typically goes hand in hand. So we want to have trustworthy machine learning, and we are studying methods to explain. So we use information theory to explain or to define explainability, to quantify explainability. But today I focus on our main research agenda, which is network federated learning. And yeah, in a nutshell, we try to organize data models, statistical models, for example, probabilistic models, and the corresponding computation. For example, when you compute the fit, when you solve a maximum likelihood equation, you must compute something. And we want to represent all of these things using the same network structure. So the data, the model, and the resulting computations, they're all happening over a network structure. But just to give an overview or to orient ourselves within the vast field of machine learning. So I'm a assistant professor for machine learning, but my parents' house academic wise is signal processing. So you will sometimes hear signal processing terms and machine learning terms. You can sometimes think about signal processing the same as machine learning. And within machine learning, we look at federated learning as distributed ways. So we have collected data, and the most basic approach is basically to collect the data at the central unit and train a model using this collected data. But we are interested in a networked form. As I said, we want to do also the computation over the network using some form of message passing. I will talk in a second, or let's say a few minutes more about message passing algorithms. Okay, so being a subset of machine learning, we follow the basic principle of machine learning. So this is what I try to burn into the heads of my students in all my courses. I ask them almost every lecture, what are the three main components of machine learning? And I try to explain and myself to research and understand machine learning as a simple combination, or as the simple principle of combining three components. So we have data, of course, maybe the main component data, it could be numbers, typically numbers. So until including my postdoc phases, I mostly looked at numeric data, it's signals. So I did signal processing, sensor measurements, everything numeric. But there's more data. There's text documents, there's networks, and data in the most general form I think of data as collections of data points, of atomic units of information or objects that can carry information. And what we do in machine learning, we try to make sense of the data. We want to learn something. And how do we learn? We learn by interpreting data, and we interpret data by fitting a model, trying to fit a model to the data or to summarize the data using a simple model. And there are various examples, linear models, decision trees, neural networks. These are all examples of different models that we try to fit to a particular data set. And how do we do it? How do we fit? Well, we need to measure somehow the quality of a model or the quality of predictions. And for this, we need the third component, a loss. In the most general sense, a loss is just a form of feedback that tells you hypothesis 1 or model 1 is better than model 2 or not. You need these three. I find that you really need to have these three components to do machine learning. So what we now do before now explain how we take this what are the specific design choices for network federated learning. Here, just one simple illustration of machine learning, which you might not call machine learning, but I would say that's the prime example of machine learning. It's fitting a straight line to data points. Like a data point could be a day. So a data point is a day. And you have properties of the day, like the minimum daytime temperature. And what you want to predict is the label or quantity of interest, might be the maximum daytime temperature. And how do you learn a predictor? Well, you could try out a straight line, try to fit the straight line to some data points that you can get nowadays easily. With a few lines of Python code, you can download weather observations on a minute scale or even finer scale for the last 100 years from the Finnish Meteorological Institute. So that's plain old machine learning. And that's the same idea, or that's the same principle behind all this deep learning magic. You just use nonlinear functions that are represented by signal flow charts, and you call the signal flow charts artificial neural networks. But what you do, you tune the parameters of this artificial neural network to fit a training data set, so to minimize a training loss. Okay, so that's plain old machine learning. However, we want to do better typically. We are not interested in learning a single model, learning a single predictor nowadays. What we want to have from machine learning is a personalization of services. I want to learn a predictor that is optimal for me currently. For example, if I'm in Turku and want to go ice skating, I want a predictor that takes into account that I want to go ice skating. So I'm really keen on getting a precise prediction of the maximum temperature, in particular if it's larger than 0. Otherwise, I will not have fun with ice skating. Or if I'm in Tampere and want to go cycling, then I might not so much interested in a precise, or I might not so much interested in label being larger than 0 or not, but label larger than, or maximum daytime temperature larger than 20 degrees or not. So we want to have different predictors. We want to learn different predictors for different persons. We want to personalize these predictors. And here also the weather gives us an example of how to do this using network data. Because we don't observe, we don't have a single weather station, also not in Finland, and also in other countries, at least in Austria, I also know that we have a whole network of weather stations. So you have network data. This is now already the first component of machine learning, data. So we now talk about a specific form of data, a particular type of data, which is I call network data. So we have collections of local data sets. So these local data sets might be the observations at the weather station in Helsinki here, then here the observations of a weather station. This might be Tampere, and in the north we have some weather stations in Lapland, or here maybe Oulu. So each weather station is one local data generator. And these local data sets are related by a network structure, which is the most basic way to encode or to represent similarities. We might say these two weather stations here in the south, they have similar statistical properties because they're in the south. The weather might behave similar. Whereas if we look at the data set collected in Helsinki and the data set collected in the outmost north of Finland, they might be statistically different. And one way to encode these similarities, very elegant way, is via a graph structure. Okay, here another example of network data, not only weather, but also images. In particular, this ImageNet, as the name already suggests, is a network structured database of images. And this was very crucial for the early success stories of deep learning, because they use this large database of images along with a taxonomy. So these images, they are not completely unordered. So it's not a bag of images, but it's a structured a hierarchy of images. So we have here a tree structure as a network structure. Another example, language, natural language, WordNet. So the words, data sets could be a text document or a word. A data point could be a single word. And different data points are related by similarities. For example, words that are nouns might be more similar to each other than words that one word is a noun and another word is a verb. Or if they are synonyms. So we call this then synsets, which are sets of words or collections of words which mean similar things. And here also you get rather naturally a network structure. Okay, maybe the largest example of a network data set is Wikidata. So maybe some of you know about Wikidata. It's basically the database behind Wikipedia. Every article you can click on, I think on every Wikipedia article you find on the left a menu item, Wikidata entry for this Wikipedia entry. So all the information in Wikipedia is stored in a network database called Wikidata. This is another example of a network data set. Okay, a bit more exotic, at least for me, because I didn't study medicine yet, but it seems diseases can also be organized as networks. So we have these comorbidity networks where each node in the network represents a disease, and you connect diseases if they occur often, if they co-occur often in patients. This is then used in a new or a discipline called network medicine, but I will not talk more about network medicine yet. Wireless sensor networks, yet another example of network data. Everything we read via a sensor, like a temperature sensor, is a local data set, and the statistical properties, the time series properties of temperature measurements at a certain location, they might be similar for sensors that are close by. So a spatial proximity might give rise to a network structure here also. Okay, yet another example, when you cut an image into smaller patches, or these are sometimes called anchors in computer vision, then you could say each anchor here, each patch subset of pixels is one local data set. And you could say, well, if these patches, if they are overlapping a lot or nearby in the image, then they might have similar properties, because all these patches here, for example, show a sky with a bit of clouds. So if you then learn for such a patch, what is there, a Gaussian Markov random field, or somewhat related, a histogram of gradients statistics, then this might be similar for these data sets which are nearby here, these patches or anchors. Okay, so this was just to motivate our abstraction. In the end, what we have is a graph. We have an undirected graph, which we call the empirical graph. And the nodes in this empirical graph represent local data sets. So some local data generator, like a person, like a human being during a pandemic, generates data. And we have some notions of similarity, which we encode in these edges. So each edge here is interpreted as a similarity relation between the connected nodes. And we also quantify the similarity. So this is a weighted undirected graph. We also have edge weights. We also quantify the extent of similarity. And in this talk, I assume this network structure given. There's a whole bunch of exciting work. I guess also many of the audience here work in this field about learning the network structure. So there are principled ways to learn the network structure. For example, fitting a probabilistic graphical model, or having some physical model for propagation of phenomena. So there are principled ways to learn this network structure, and we also have some ideas how to do it. But today I will not talk about this. I assume that the network structure is given. So we know the network structure, for example, from some meteorologist who knows this weather station and this weather station, they are on a plain, there are no mountains in between, so they should see very similar statistical properties of the weather observations. Okay, so yeah, by the way, I mean, you could say this is a challenge, a limitation, that we assume this graph structure known. On the other hand, it might also be a feature. So here is where you can bring in the domain expertise. When you work, for example, with co-morbidity networks, where each node represents a disease, then I have no idea, basically, which diseases co-occur often. But a doctor might know, okay, these two diseases, you should connect them by a strong link. So here you can bring in the domain expertise. Okay, so second component. What is the second component in machine learning? First, the most important component is data, but data by itself is useless. You can look at it, you can send it around, but you need to interpret it. So you need to fit the model. And here we use, of course, networked models. One example, so in principle, a networked models is just a rather naive approach or intuitive approach to use whatever models we have, we are familiar with. So some of us are familiar with decision trees, so you take decision trees. Some of us are familiar with linear models, so we use a linear model. And we just use, we donate a separate model to each local data set. So that's the basic idea. We attach to each node not only a local data set, but also a local model. But then somehow we need a way to couple these different models. So we need somehow couple the model for this ith node and this jth node. And one of the most elegant approaches to do this, and which I just heard about and don't understand much about it, is called sheaths on graphs. So a sheaf on a graph, as I understood from this nice introduction, which I show here the link to, is basically a sheaf is an assignment of a linear space, which is maybe the most popular model we use in signal processing and also in machine learning. Under the hood, a linear model. So a linear space, we assign a linear space to each node. For example, here, the linear space might be let's assume this is a sensor. So this node here represents a sensor, and this node here represents a sensor. And this sensor has a certain range, sensing range. And the sensing ranges are these polygons, these field polygons here. So one linear space might be the space of all fields, like profiles of temperatures over space that is supported on this sensor range, the orange one. And another linear space might be the space of all field profiles that we can sense on this blue domain. And how do you couple them? You couple them by requiring them that on their intersection between two connected nodes, they must agree with each other. And this is what is called in the sheaves, what is this? Restriction maps. So the sheaves on graphs is basically the precise language, mathematical language, to require that these two linear spaces that represents data that you can measure to agree on these similar nodes. Okay, but we bake smaller buns, so to say. We only use parametric models. So we think of a networked model as vectors, vector-valued graph signal, you might say. So we just assign to each node a model that is parameterized by some numbers, which we stack into a weight vector. So this could be a linear model. This weight vector could be the parameters of a neural network, or these weight vectors could be the parameters of an exponential family, if you like probabilistic models. So just some parameterized model. I keep my discussion very abstract, so you can use basically any parameterized model. But of course, the more you know about the model, like convexity properties, the more you can say, the more analysis you can do. And we will bring in these assumptions at the later point. Okay, but again, we need to somehow couple these weights, parameter vectors at similar nodes. And we can do this in similar ways. And one rather generic way is what I like to call a generalized total variation. So we require the differences. So yeah, this is our basic assumption, that the weight vectors, they live all in the same space. So they all have the same length in particular, which means we can compute the difference. This, when you use sheaths on graphs, you don't have this restriction. That's what is cool about the sheaths on graphs, but it's too hard for me at the moment. So I just use the same vector length at each node. So I can compute differences. I can compute something like it's like a gradient, a discrete gradient, the difference over connected edges. And then I can use some penalty function, which I call phi here. And this is typically a function that increases in a norm of this difference over the edge. So what I then want to do is I want to push this generalized total variation to be small. So this is like a regularization. Yeah, two special cases that I would like to mention here. When you use the Euclidean norm, then this is sometimes called the total variation. Or when you use the squared Euclidean norm, what you get when you plug it in. So this is just then, you can rewrite this as a quadratic form in the Laplacian. And this second choice here is often used, or I would say is one of the most popular choices in signal processing so far, in graph signal processing, because when you penalize this graph Laplacian quadratic form, what you essentially do is you require the weight vectors to form it's called a low pass signal. So you require the weight vectors to vary only over few edges and to be essentially flat on well-connected subset of nodes. And one way to express this is via low pass constraint. Yes, so okay, so here one specific example, as I already mentioned, in graph signal processing, you look at this signal in noise model. So that the parameter at each node, you have a single parameter or a single weight, which is corrupted by noise. And what you observe, the graph signal, is a noisy version of your weights or parameters at each node. And then what you often do, or what you often see in many papers, you put a low pass constraint. So you constrain this generalized total variation with the squared of the differences. And as I already indicated or tried to provide intuition, requiring this total variation to be small essentially means that you require this weight to form a low pass graph signal. Okay, but yeah, so our work so far, we try to be as general as possible. So we completely abstract we try to abstract as much as possible from the precise form of the model. If it's a linear model or an exponential family, all we need is a loss function. Remember the third component of machine learning, a loss function. So we have data, we have network model in the form of parameter vectors, one for each local data set, and we need a loss. So we have also a local loss function. And this local loss function encapsulates all the nitty-gritty details that we have about a model. I mean, if you use as a model like graph signal processing, I mean, this model is not too complicated. So it's a single signal in noise model, but it can be basically anything that you parameterize with a finite number of parameters, and for which you know to evaluate the quality of a particular choice for the parameters, which is a loss function. So whenever you have a loss function, you can give us a loss function, we can help you further. Okay, so yeah, and then it seems natural, we have the loss functions for the local models. So we would like to minimize it, and it seems not a bad idea to minimize the average. Like in empirical risk minimization, when you have several data points, you look at the average loss. So let's minimize the sum of these local loss terms plus, and the second term here is what couples the local models. So the second term is the generalized total variation, and we modulate this second term by some regularization parameter lambda. So the larger we make this lambda, the more emphasis is put on this generalized total variation term. And after some critical value for lambda, you force the resulting weight parameters or parameter vectors to be constant, to be the same for all nodes. So there's some critical value for lambda, which depends on the local data sets and the local models. But if you choose it beyond that point, you kind of iron out all differences over the local model. So you learn one single model for all local data sets. So this would be basically plain old federated learning. And actually it might be useful. It might be useful in some applications. You might say, I want to learn a single model for all data points, and I want to do it in a distributed way. And I will now show you some ways to do this in a distributed way. And you can do this in our setup just by choosing lambda large enough. On the other hand, if you make lambda smaller and smaller, so in the extreme case, you make lambda equal to 0, you completely ignore the coupling and you just, it breaks down into separate optimizations of the individual loss functions. And you might also be interested in doing this. On the other hand, our approaches, they allow for having these loss functions only at the few nodes. So we can kind of bridge nodes where we don't know a loss function. Or for some local data sets, for example, you don't know labels of data points. So you cannot evaluate the loss because you don't have the labels. So this is something like semi-supervised learning setup. And our approach allows for this set of loss functions, this M, calligraphic M, to be smaller, actually to be a vanishing fraction of the whole network. It turns out when you, for specific choices of this penalty here, particularly if it's not the squared Euclidean norm, if it's something like the one norm, then you can get reasonable results with this GTV minimization, even when this set of sampled nodes is a vanishing fraction of the whole data set. And this might be interesting when it costs, in the sense of money, when it costs to collect labeled data points. Okay, yeah, so here the general form of GTV minimization. Let me mention two special cases. One special case when the penalty is the Euclidean norm. This is a network lasso. So this is known as network lasso, was introduced recently or popularized in a paper by Stephen Boyd and co-workers. Another example is called MOCA. So this is one of the seminal papers in the machine learning community about federated learning. So MOCA is GTV minimization using the squared Euclidean norm. So these are two special cases of GTV minimization for specific choices of this phi. But our approach provides a lot of flexibility. For example, I have seen now more and more works or applications where it might make sense to use different, to take the different entries of W into account in a different way. So to put different emphasis on some parts of the weights. For example, when these weights are weights of a neural network, then there's a difference between the weights in the first few layers and the last few layers. And this phi here gives you the flexibility to put, for example, more emphasis to enforce the first layers to be flat, so to be constant over the whole network, where the last layers you allow to adapt more for different parts of the network. So this is sometimes called transfer learning. And this phi allows this flexibility. So this would, for example, you could implement this phi as a quadratic form with a positive semi-definite matrix, where this positive semi-definite matrix is weighting put different weights on different parts of the weight vectors. Okay. So these are two examples. Yeah, just as I already pointed out, this GTV minimization is one form to do multitask learning. You can think of learning the weight vector for a single node for a local data set as a learning task. So each node corresponds to one learning task. And when you solve GTV minimization, you solve all learning tasks at once, simultaneously in the network, using distributed computations. It's also a form of semi-supervised learning, because our approach works also when you observe, when you know the local data sets only at few nodes, at this set M, calligraphic M. We call it sampling set when I'm a signal processing person, and I call it training set when I'm a machine learning person. Okay. Also, a nice interpretation of this GTV minimization, it's a form of locally weighted learning, or so a more general form of locally weighted regression. Because what we do is when we solve this GTV minimization, we will see later, the weights tend to be constant over clusters. So as soon as there is a subset of nodes which are well connected with each other, when you solve GTV minimization, the resulting weights that are the solutions of GTV minimization will be constant over this cluster. And this means equivalently, you could think of learning a single model by pooling all the local data sets in this cluster and ignoring all the others. So this is kind of a dual view, or the interpretation is to do locally weighted learning or locally weighted regression, where the weights are 1 for all data sets in the same cluster and 0 for all data sets outside the cluster in a different cluster. So what we do is one particular form of a quite elegant way of locally weighted learning. Yeah, and this locally weighted learning is around already for long. So this is since, I would say, 30, 40 years around. Okay. So shall I take questions on the fly, or how is the procedure?
Yeah, it's up to you. If there's an urgent question that is important for people to understand, you can take it.
Yes.
There's some question about clusteredness, some examples for clusteredness. But, yeah.
Yes. So clusteredness. What do I mean by clusteredness? It means basically nodes, or that there are. If you have an empirical graph where there are some nodes which are well connected with each other, and actually I will talk about a quantitative measure for clusteredness in a few minutes in later slides. So I will show you how to measure clusteredness and how to define it precisely. Okay, so now where are we at the moment? So we have formulated a generalized total variation minimization. And that's basically what is the result of modeling some application as a machine learning problem. At least in many cases, the result of this modeling phase is an optimization problem. So you have a loss function, you want to minimize the loss function. You also have some model assumption, and this modeling assumption somewhat implicitly is in this regularization term, in this case, in this GTV term, which means clusteredness in our case. And you have data to evaluate the loss function. So we bind these three components together to get an optimization problem. This is sometimes called a regularized empirical risk minimization problem. And that's then one machine learning problem. So this is sometimes referred to as a machine learning problem. And we try, and then in machine learning, we're always interested in two things. Once we have a machine learning problem, or at least I am interested in two things. The computational aspect, how do I solve this optimization problem efficiently? And the second aspect, are the solutions any good? So even if I have a super powerful optimization method that finds the optimum, how do I know that the optimum is any useful of this problem? And I will now discuss these two aspects in a bit detail. So the first aspect is the computational aspect, which is the question, how can we solve GTV minimization efficiently? In particular, how can we solve it using in-network computation, distributed computation that is carried out, for example, in a peer-to-peer fashion over low-cost devices like Raspberry Pis or whatever you like to play with. How can we do this computation in a form that is robust against node and link failures? So we might have sometimes nodes that don't respond. So how should we continue? And so one special case is here also the problem of stragglers. So the computation, the local computation takes so long that you cannot keep track with the others when you update the model parameters. This is sometimes referred to as stragglers. And I will now show you how you can or how these aspects are addressed by recent methods for solving this optimization problem. So as a first example, as kind of a warm-up, I consider the special case of graph signal processing. So you have the local model is that the observed signal xi is a noisy version of the true signal or the parameter you're interested in, this wi. So what you do is you minimize the sum of squared errors over the observed nodes plus a regularization term. And let's assume we use this graph Laplacian quadratic form. And for this case, when you look at the optimality condition, which basically is the zero gradient condition, this amounts to solving a linear system of equations. And this linear system, or the system matrix L here, is basically reflecting the network structure. It's essentially, or it's very closely related to the graph Laplacian. And there, to my surprise, there's a still quite recent line of work that basically explores the absolute limits of how far you can, or how efficient you can make this solvers. And there's one of my heroes on linear algebra, Dan Spielman, from, I think he's in, where is he, in Yale or Princeton, I'm not sure. He is kind of pioneering this line of work. He came up with rather efficient methods to solve this. So this is, you can consider this as a technology to solve linear equations. Might be non-trivial for your given case, but we have pretty good understanding how to solve linear equations in general. Yeah, for a bit more general form of GTV minimization, it might be useful to bring in the concept of duality. And this is then the main theme of the much of the rest of my talk, the duality, because it turns out that the dual of GTV minimization has a very nice interpretation as a network flow problem, a network optimization problem. So if you bring in dual variables, which are basically the differences over the edges, the differences in the parameter vectors, so that these dual variables live or are supported on the edges. These dual variables live on the edges of the empirical graph. The parameter vectors, they live on the nodes of the graph. There's a very recent work that uses these dual variables to come up with a primal dual gradient method for such GTV minimization problems. And so these works show actually you can solve these methods pretty fast. So this is known as linear convergence, which is quite fast in general. And these are not too expensive iterations. So these iterations, they amount to simple local computations and then some spreading, diffusion of the results, of the local results. Okay, but these methods here, these gradient-based methods, they of course need gradients. That's why they are called gradient methods. So, but what can you do when you don't have gradients? So when the objective functions are non-smooth, and there's also I would say it's already quite a technology. It's very mature type of optimization algorithms which go under the name, for example, ADMM, alternating direction method of multipliers. You can write down the iterations for many problems, for many choices of these loss functions in nice closed form. And these methods enjoy really strong guarantees, robustness properties, which I will talk in a second. But before that, I would like to develop more this duality approach. So our focus of my group is not on ADMM, but a close relative, which are called primal dual methods. And these primal dual methods, as the name suggests, they look at the dual of GTV minimization. So it turns out that you can formulate another optimization problem that is called dual to GTV minimization, and which has basically the same optimal value. So there's these two optimization problems, this dual problem and the original GTV minimization problem, they are in a very specific sense equivalent. So once you know how to solve this GTV minimization problem, you know how to solve this dual problem and vice versa. And what is nice about this dual problem, as you will see in a second, it can be interpreted as a flow optimization problem. So this is when you write out these components of this dual problem, so this G star, these are called convex conjugate functions. Here you need a bit of convex analysis. When you look at the convex function, so here this black one, there are at least two ways to represent the convex function. One is, writing down the convex function. So for each argument x, what is the function value? That's one natural way to represent the convex function. But another way is to say this convex function is fully characterized by its epigraph. So by all the points that are above the graph, and this epigraph is convex because it's a convex function. So you can represent it as an intersection of infinitely many half spaces. And these half spaces here, or hyperplanes, the boundaries of the half spaces, they can be again parameterized by a vector, which we call a dual vector, u. So you can think of the convex conjugate function as being the offset for these hyperplanes when you prescribe the slope of these hyperplanes. So this function f star of w, or I should have called it f star of u, maybe. These are the offsets for these hyperplanes. And they provide a fully equivalent representation of this convex function. And we can then just plug in these convex conjugates, essentially, and get a dual of GTV minimization. And the nice thing or interesting thing about this GTV minimization is it's a special case of a flow optimization problem. And this flow optimization, or more generally, network optimization, this is also quite a mature field. So this connects all what I have talked about so far, graph signal processing, semi-supervised learning, multitask learning. It connects all these fields with network optimization. Okay, so I might, for the sake of time, I might skip these details about working out these optimality conditions. In a nutshell, you try to solve the primal and the dual problem simultaneously. So you come up with optimality conditions, which is basically a generalized form of a zero gradient condition. Remember, for a convex differentiable function, to find the minimum, you have to set the gradient to 0. And for this pair of primal and dual optimization problems, you have something similar, which is of this form here. So this is an optimality condition. And you can solve this optimality condition by using fixed point iterations, which is also called a proximal point algorithm. So this again is very established, and I pointed here to quite well-written references. So if you want to learn more, have a look at this nice tutorial on this primal dual methods. And again, you can write down the resulting algorithm. It's an iterative algorithm, so it proceeds in iteration. And in each iteration, what you do is you do first local computations. You start with a current guess for the local parameter vector and try to improve it a bit, or improve it kind of optimally given the current knowledge. And after you do this local or node-wise, I call this primal updates, and also these dual updates. So you do these local updates for each node and for each edge. You spread out these local results. So there's then some a spreading or a diffusion step following these local updates. So this, in the end, is a message passing algorithm. So it's distributed. It can be implemented in a decentralized fashion by passing messages over the graph. Yeah. What is nice about these primal dual methods is we have a rather good understanding of them already. For example, we know what happens if some parts of the optimization problem are noisy. For example, you might have that your network structure is obtained by coin flips. So as a realization of a random variable. For example, when you use random graph models. So when you use random graph models, the edges, they are the result of random experiments. Or also when one popular model for data in machine learning, you assume that the data, they are realizations of random variables. So this basically means you don't observe the actual loss function, but you only observe a noisy version of the loss function. And also you don't observe the actual network structure, but only a noisy version. And this might also be because you randomly sample the network. So you don't do the updates at all nodes, but you randomly select nodes where you do the updates. this way you also bring in some stochastic noise. And it turns out that this primal dual method is very graceful, has a very graceful behavior when you have these stochastic perturbations. So there's a line of work that studies this primal dual methods when they have access only to a noisy version of this objective function. Okay. Yes, somewhat related to this robustness against random noise is, of course, an extreme case of random noise is when the node completely fails, or if it's delayed, when you have a straggler. So this robustness against random noise, or robustness in general, almost implicitly brings you, or simultaneously brings you robustness against node failures or link failures. Yeah, and also what you can also use this robustness for is you can artificially inject noise. Why might this be useful? This might be useful because you want to ensure privacy. You want these updates that you get. So remember, you do these local updates at each node. At each node, you do a local improvement of the model parameters. And when you improve these model parameters, you somehow read out information of the local data set. But you want not too much information to be leaked out then when you spread out the updates in the spreading step. So what you can do is you add a bit of noise. There are at least two ways to add this noise. Well, add a noise term, add a noise variable, or quantize. Use quantization. And this techniques is known as differential privacy techniques. So this robustness of the primal dual method, this kind of very established convex optimization method, offers you immediately a possibility to do privacy preservation by adding noise a bit, so to not leak too much private information from this local data set, but still allow the overall process to learn good model parameters. And of course, there's a trade-off. We call this sometimes utility privacy trade-off. So the more noise you add here, the more you protect the privacy, but the more noise you add, the more noisy your results will become. Seems natural. Okay, so the bottom line here is there are established ways to compute the optimum of GTV minimization in a distributed, robust, and privacy-friendly way. However, it's the second question. The statistical aspects. Are the solutions itself that we then finally get, are they any good? Are they useful? And this question is answered by sampling theorems in signal processing. And I assume that many of the audience today have actually contributed to signal processing in the form of sampling theorems. And in machine learning, we call such type of answers generalization bounds. So just to give you an idea, I picked out one very nice approach that is based on uncertainty principles. So the question is, which nodes do I need to observe, or how many local data sets do I need to observe to have any chance to learn the parameter vectors, the true underlying parameter vectors? And for this, of course, you need to assume a model. So again, second component of machine learning, you need a model. One model is to assume that these weight vectors, they are, we call this band limited or low pass signals. This is a generalization of signal of discrete time or time signal processing. So you assume that these weight vectors, they essentially have a small total variation. So this requiring this total variation term to be small essentially means that the bandwidth of these weights considered as a graph signal is small, it's not too large. And then there's a beautiful result recently that tells you when you know that the bandwidth is not too large, so is small, then the kind of the spread in the node domain cannot be too small simultaneously. So when you have a very small bandwidth in the frequency domain, so when you make this bandwidth small, then the signal must be spread out widely. Essentially, this means that the weights are constant over all nodes. And what you must do, you must sample nodes that are not that are kind of not too far away, not more far away than this basic uncertainty principle tells you. So this uncertainty principle tells you when you have this or that bandwidth, then the spread of these weights around this node, for example, cannot be much larger than 4. And 4 as a distance means the shortest path, the number of hops that you need in a shortest path. And this can guide you to choose the next point or data set that you want to sample. You must hop at most 4 hops, and then you must observe the data set again. This is one type of sampling theorem. Here, a bit more convoluted result for machine learning, generalization bound. So what drives this generalization bound is essentially here the eigenvalues of the graph Laplacian. So this is just another way to require the graph signal or the parameter vectors to be a low pass signal. So this is not too different in spirit from this requirement, from this low pass requirement here, but it's formulated in terms of the eigenvalues of the graph Laplacian. And this is a general trend or a main theme in existing results. They rely heavily on spectral properties of the network or of the graph in the sense of the eigenvalues of the graph Laplacian. And here now, this is my last main point I want to make. We take a different approach. So our approach is not via the spectrum, because here at Aalto, at the time I came here, we had very strong groups and still have strong groups on networks and how to cluster networks. So I wanted to look at this directly from the nodes. So I don't want to compute the spectrum of graph Laplacians. I want to see this model in the network in the form of cluster structure. And so how do we do it? We use this duality between GTV minimization and network flow optimization to require the existence of flows. So what it turns out is we can ensure that the solutions of GTV minimization are useful in the sense of being constant over well-connected subset of nodes if we can find a flow, a network flow, that saturates the boundary edges. And this is how we define a cluster. A cluster is a subset of nodes such that we can route, we can fill all the edges that go out of that cluster completely full with some water or any fluid. Yeah, by the way, I forgot to mention, in our approach, we use these weights, the similarity weights between connected nodes as a capacity, as the capacity of flow or link capacity. So we want to saturate the boundary edges and only allow the flow to enter or leave the network via the sampled nodes, via the sampling set. And it turns out if we can find such a flow that saturates the boundary edges and only leaves or enters the network on sampled nodes, then the solutions of GTV minimization are constant. So all the weight vectors here in this cluster are the same. Or put differently, we are able to pool the right data sets together to learn one single model for this cluster that is separated by a saturated link from that cluster. So that's the main idea that drives our approach so far. Yeah, so once we have found such a flow, and kind of our sampling theorems in spirit are existence theorems. They tell you, they look at conditions that guarantee the existence of such a flow that saturates the boundary edges and gets out or into the network only via sampled nodes. And if this works, we have really cluster-wise pooling. So we collect the right data sets with each other. We do, as we train the local models, we at the same time pool the right or the relevant neighbors of each local data set with each other. Okay, and yeah, also a nice interpretation, the amount of flow that goes out of the sampled nodes must be compensated by the gradients of the local loss functions. So yeah, it becomes now a bit more challenging because the gradient is a vector. So we talk about vector valued flows. If the weight is a single number, like in graph signals, when you have a single graph signal, this weight is a single number, but we typically have vectors. So this is a vector. And here this result relates, or we can show that the flow that leaves or enters at the sample node must be equal to the gradient of the loss function at the solution. And by this, we can explore the relation between the geometry of the local loss function, for example, some bounds on the Hessian, on the second derivatives of the loss function, and then the network structure, like the bottlenecks, how much flow can flow through this bottleneck, such that we can cover it by the gradient, or how steep does the loss function have to be such that it can compensate this flow while not moving too much away from the local minimum of the loss function. So this relates the geometry of the loss functions with the geometry of the network. Okay, I think I'm running out of time. How many minutes do I have?
Yeah, you can have a few more minutes, let's say 3 minutes.
Okay, very good. So yeah, just to wrap up, we measure the clusteredness by the existence of network flows. For example, we can measure the clusteredness here of this two-cluster network, toy network, by the amount of flow, rho, that we can route over this edge, where this edge, the capacity of this edge is its weight, such that all the other capacity constraints are satisfied and the flow conservation is satisfied, and it can only exit here. And so if we parameterize then the solutions or the resulting accuracy using this cluster connectivity, we have shown recently that we can pretty much precisely predict the behavior of network lasso or GTV minimization methods. So we can predict the threshold of the amount of clustering until it works. And at some point, you have too many edges between the two clusters. So this connectivity becomes smaller and smaller, and then it doesn't work. So you're not able to resolve the clusters. You can only resolve the clusters if you can route only a small amount, if there's a small bottleneck between the clusters. Okay, then we also have looked at, nice, good, I can draw these nice results, but does this also work? Does this only work for this toy graph, which is completely useless for many applications? Well, we have shown that this assumption works for certain parameter regimes of the stochastic block model. So stochastic block model, you might say, again, a toy model, but maybe a bit more reasonable toy model. And we can also here predict pretty accurately the phase transition for the stochastic block model parameters that allow GTV minimization to identify, to resolve the right clusters or blocks. Okay, yeah, I just skipped. The nice thing about this flow picture is it allows you to use very established results from graph theory. So you just have to count cuts, or you have to estimate cut sizes. And there are beautiful results by Karga about sampling methods, so randomized methods to estimate these cut sizes. And these are pretty simple arguments then, once you subscribe to this flow picture. Okay, just to wrap up now, we have formulated network federated learning as GTV minimization. Two special cases are network lasso or MOCA. We can solve this minimization problem using rather established mature primal dual methods, which are robust against various forms of imperfections or errors or stochastic noise that you might bring in intentionally to protect privacy or to reduce computational complexity. And we have started to characterize conditions, for example, parameter regimes of stochastic block model, such that the solutions of this GTV minimization are kind of capturing the true underlying cluster structure. And yeah, one of the big open questions on our future work is about learning the network structure simultaneously with learning the local parameter vectors. Okay, so yeah, if you want to dig deeper, I just want to point out the seasonal school on network federated learning, which will start end of March. And here we will start really from the basics: data model loss, gradient descent, and build up the theory and methodology all the way till we can understand total variation minimization. Okay, thanks a lot.
Okay, thank you, Alex, for this interesting talk, connecting many different fields. Okay, so it's time for some questions. So maybe we can start with the chat to see what is there already. So I think there was also a question about, in the case of sheaves on graphs, what exactly are the node values then on the graph? I guess they are subspaces then, right? Or...
Yes, exactly. The sheaves, with sheaves on graphs, you have at each node not a vector or a value, but a subspace, a space.
Right. Yeah. And then related to, yeah, so you have these local models, right? So does it only work when your local models are all the same type, or so there's a question, can it be also when these models are serving a different tasks? So suppose can one be a CNN and the other one be just a linear model? Does it still make sense then?
Yes, so all we require is that the weight vectors are of same length. So
yeah.
otherwise,
let's say conceptually, does it, I mean, it might not make sense to have these W's then similar, right? Because, okay, even if they're similar, the model might be completely different because the structure of the model was different.
Sure. This might simply not work then, yeah.
Yeah. Okay. Then there was a question about, can we know Bregman methods? I guess that's related to the optimization of your cost function, I guess.
Yes, so I'm not an expert in these different variants, but I assume yes. So there are a lot of design freedom in the design of these proximal point algorithms.
Okay. And then you also mentioned this in the end. So you have vectors, right, on the nodes of your graph. So how do you define then bandwidth in that case, if you have not single scalar values but vector values?
Yeah. So what I talked about here. This bandwidth, yeah, this only applies to scalar valued weights. I don't know precisely how I wouldn't know precisely how to extend this to vector valued parameters.
I guess that's what you mentioned earlier, right? So you would take just the L2 norm there, L2 norm squared, right? Or
yes.
guess, right?
Yes.
So it's some kind of average, right? Average bandwidth or something.
Yeah. But I remember from my PhD times, you can extend lots of this duality, time frequency duality also for vector valued signals. But I didn't look at this yet.
Yeah. Okay. So any other questions from the audience? So you can either write it on the chat or unmute yourself and ask the question. So maybe I can start with, yeah, so if you compare this to classical federated learning, as far as I remember, so there you have like a fusion center or something, right? So it's like a star network.
Yeah.
So if you would apply, let's say, your method on a star network, would you get the same result? Like, then you'll get like the average of the W's or something, right? Or all the nodes would have the same W, I guess.
Yes, so this you can achieve with choosing lambda large enough in this setting. When you make lambda larger than a critical value, you flatten out the weight vectors. They are all the same then over the nodes.
Okay, yeah. And related to your last point, so what if you would just first cluster the graph and then try to just use that data within a cluster to find the W? Would that be worse than what you obtain? Okay, you find kind of jointly the clusters and the W's, I guess, right? So
yes.
But what if I would do separate in 2 steps, first the clustering, and then I find locally or per cluster the W?
Yeah, so the very good point. This might work actually, but I'm not sure if the clustering. How would you exploit how would you cluster?
Yeah, I just use some standard clustering method, and
Yeah, but we assume that the data is given in the form of local data sets, which are abstracted kind of. There's an API level where we just use a local loss function. So how would you input these loss functions into a clustering algorithm?
Yes, that's true. Yeah, it would be then. Yeah, the loss would be different. Yes.
Yeah, but what you could do, of course, if the local data sets are of some simple form like a tabular data, then you can do like dimensionality reduction. You can project it down to dimension 2, and then you can cluster it by hand. Yes, so you can do this. But in our case, we guide the clustering by by doing these local optimizations.
Yes. Okay. Clear. Yeah. So there was also a new question in the chat, like how do you choose the next node to deliver the estimation based on the current node? Gossip algorithm or some random walk-based mechanism? I'm not sure what this is. Yeah, what part this is related to.
Yeah, in the standard formulation, we spread out the results to all neighbors. So yeah. there is no selection choice, or there is no scheduling. Then what you can do is then randomly select neighbors for which you only do the update. And this is then what I mentioned here in the stochastic versions, or in the sampling with arbitrary sampling.
Yeah, that would get close to kind of gossiping, right? More or less.
Yes.
Or, right.
Yes.
Any other questions?
Maybe I have just a quick question. So it's clear the model and everything, but like in a real, like if you would use, let's say, these approaches in a real context, like when is the case in which you want the parameter of the model, like the W vector, to be the same in different nodes? For instance, if you need to like weight the features that you have, why do you want that all the features for different entities are the same? Like, if you can give me a real scenarios where you want this, like.
Very good point. Yeah, why do I want this pooling? So one, maybe the most relevant question answer in my case, because the local data set itself would not be enough. So you need to pool, you need to have more training data.
Okay, but then but you in every node you are going to learn something. So when you then use the regularization term on the right part to make them similar, if one has few data, doesn't estimate well the parameter that you want, and you want to shrink, like the minimization to be, you want similar values in connected nodes. So then you optimize every local data set, but then you want them to have the same parameter. So yeah, like in which context, like in which scenarios might this be applied, for instance?
Yeah. Well, if for example these nodes represent customers, I mean, this is one main application domain of machine learning is to recommend products, and these customers would then behave similar, or would be similar. Somehow you have a business analytics expert looks at your customers and says these four guys or girls, they are very similar. So it would then make sense to learn similar models of a personalized recommendation system.
Okay. Yeah. Oh, okay.
Yeah, and then I mean here this is the extreme case where you observe only one local data set in each cluster. So this pooling doesn't really help here much, because there's not much to pool in the same cluster. But if you observe, in some applications you might observe a bit of data or a bit of information at every node, but very noisy. So what you would like to do is then to average over more nodes or more local data sets. And there, when you enforce the weight vector to be constant over this cluster, this means that you essentially pool all the local data sets in the cluster. So you have more data to average over.
Okay. Yeah, maybe in that case will be necessary maybe to use the regularization lambda to be personalized in when you weight the differences, because maybe if one node has very few data, you have that the model is not, the W is a bit not useful in order to have similar values in connected nodes. So maybe the lambda I there should be maybe smaller, or.
Yeah. But this you can also include in this weight term. So you can make weights larger or smaller if the similarity is high or not so pronounced.
Yeah. Okay. Thank you.
Sure.
Any other question? Okay, if not, then I think we can wrap up here. So thanks a lot, Alex, for the talk, and thank you all for attending. So there are some questions about the video and the slides. So we will put the PDF of the slides and the video on the webinar website, and also the video will be on the YouTube channel of the IEEE Signal Processing Society. So the data, the information will be available. So, and then our next talk will be on March 3. So keep an eye on that. So thank you all. And